In this lesson, we will discuss cluster maintenance and administration. After completing this lesson, you will be able to explain how to add and remove nodes in an ad hoc way. Explain how to add and remove nodes in a systematic way, otherwise known as commissioning and decommissioning of nodes. Explain how to balance a cluster. List the steps for managing services, including adding, deleting, starting, stopping, and checking status of services. Explain the procedure to enable rack awareness. List the steps to add, remove, and move role instances and hosts. Cite the challenges faced with the first version of Hadoop. Explain the features in the second version that help overcome the challenges faced with the first version. In previous sessions, you have learned that a cluster is nothing but multiple nodes working together. Planned and unplanned failures often occur in a cluster. Clusters are horizontally scalable, and you can add or remove nodes as required. In this topic, we will learn about cluster maintenance, including how to add or remove nodes from a cluster, and how to balance a cluster. You can add or remove a node from a cluster by following either the ad hoc way or the systematic way. Let's learn how to add and remove nodes in the ad hoc way first. To add a node to the cluster, you simply configure it and allow it to interact with the master. To remove a node in an ad hoc way, you simply unplug the cable of the node, switch off the node, or just issue an abrupt shutdown of the node. Although the master, otherwise known as name node, can handle an addition or removal of a node in an ad hoc way while maintaining the replication consistency, as well as the availability of data, it takes a while for it to decide on how the event should be handled. The name node will need to manage extra blocks if machines are added in an ad hoc way already had some data blocks. It has to delete them to ensure replication consistency, or replicate them again because of missing nodes. Due to these events, name node may incur an unplanned overhead. Moreover, the process itself is time-consuming. Therefore, it is recommended to add or delete nodes in a systematic way. We will now learn how to add and delete nodes systematically. As adding and deleting nodes in an ad hoc way results in overheads and consumes a lot of time, we should take the systematic approach to add or delete nodes. Adding nodes in a systematic way is also called commissioning a node. This is done by informing the master or name node in advance about the addition of the node. Deleting a node in a systematic way is called decommissioning a node. With the Cloudera Cluster admin interface, commissioning or decommissioning a node is very simple. All you need to do is click the relevant options. The tasks are performed in the background, and the node is commissioned or decommissioned. However, if you are using the Apache Hadoop cluster, you will need to perform the following tasks. Edit the configuration files, hdfs-site.xml and yarn-site.xml during the cluster setup. Recall that in the first version of Hadoop, it was mapred-site.xml that needed editing. Create empty include and exclude files. Set the properties in the configuration files to point to the include and exclude files. Start the cluster. Edit the include and exclude files and specify the nodes to be included or excluded. Issue the commands hdfs dfsadmin-refresh nodes and yarn rmadmin-refresh nodes. Issue an HDFS balancer command to ensure an even distribution of data. Update the slave files to make the correct entries of the nodes that are part of the cluster. Note that if decommissioning affects the replication consistency, the master or name node will not let the slave daemon or roles that are on the decommissioned nodes go down until the details of a replacement node for them are provided to name node. In addition to these tasks, remember to update the topology file used if rack awareness is enabled. The systematic way helps to keep a track of which nodes were added or removed and which ones were already existing in the cluster. We will learn about rack awareness later on in this lesson. Let us now view demos on commissioning and decommissioning nodes in a Cloudera cluster and also in an Apache Hadoop cluster. Adding or removing machines in an ad hoc way in Apache Hadoop cluster. In the previous demo, you learned how to set up Cloudera cluster on your machines in AWS EC2. In this demo, you will learn how to add or remove machines in an ad hoc way. There are clusters containing data and running on two machines, M1 and M3, which are the only two machines in this cluster. Hadoop allows horizontal scalability, which means you can add multiple machines. Hadoop also deals with machine failure. There is an ad hoc or systematic way of adding or removing machines. An ad hoc way of removing machines includes unplugging the cable and switching off a machine. In the cluster, type HDFS, DFS-admin-report. Which will show you the data node, how many of them are running, and their status. To remove the machine, just power it off. Now there is a single active machine that has name node, a resource manager, a node manager, and a data node. You can set up a simple script to view the status of the cluster. Once a machine is powered off, name node will not consider it inactive immediately. It will still try to contact the dead machine. After a machine is deactivated, the name node will wait for approximately 10 minutes before declaring the machine dead. If you give the command HDFS, DFS-admin-report repeatedly, you can see the last contact detail, which, in this case, will show a time difference between the two machines. To monitor the status of a cluster using a script, build up a small script using vi mymon.sh and press Enter. Type hash !bin/bash followed by HDFS DFS-admin-report and externalize through a file dfsrep.txt. Add cat to the file dfsrep.txt, a pipe, and grep live data nodes. To view the number of data nodes, type cat dfsrep.txt, pipe, and grep hostname. Type cat dfsrep.txt, pipe, and grep last contact. Save this file. mymon.sh is not yet executable. To make it executable, type chmod -R777 mymon.sh. To execute it, type /mymon.sh. Return to the previous script and type rm-rf-dfsrep.txt. Copy the previous commands and paste it. You can highlight important information in a different color and then execute it. If you type hdfs fsck/-blocks, you can check if any block is under-replicated. In this case, there are no over, under, or misreplicated blocks. To add a machine in an ad hoc manner, bring up a new machine, M2, a clone of an existing machine. Edit the IP address for the M1 and M2 machine to communicate. In the M1 machine, type cat/etc/hosts, and it will show two entries. To edit the entries, type sudo vi/etc/hosts and enter the password. Type 192.168.1.198, which is the IP address of the M2 machine. Update the machine entry of M1 into M2 and enter your password. Click the terminal icon to open it and log in as root. Type vi/etc/hosts and you'll be able to view the entry for M1. Log in as HD user and view the home directory using the command ls-all. In the directory, type ls-all.ssh. As these machines were cloned, the existing entries will not be used. To remove the existing entries, type rm-rf.ssh, followed by ssh-keygen-t, rsa-P. Generate the SSH key as seen previously. From the current machine, copy the public key to the M1 machine, which has the name node running. Copy the public key to the HD user at M1. Type yes when the system asks, "Are you sure you want to continue connecting?" Enter the password for M1. Similarly, from the M1 machine, copy the SSH key to the M2 machine using HD user at M2. Type yes when the system asks, "Are you sure you want to continue connecting?" Enter the password for M2. Once you have the SSH access, in the M2 machine, type cd/usr/local/hadoop/etc/hadoop. Type vi core-site.xml to view the config files and find out if they are empty or if they have some settings. In this case, the core file is empty. Type vi hdfs-site.xml, and you can see that the HDFS file is also empty. Copy the config file from M1 to M2. Type cd/usr/local/hadoop/etc/Hadoop. Type scp hadoop-env.sh hduser at m2 and give the path as /usr/local/hadoop/etc/Hadoop. Similarly, copy the core-site hdfs-site mapreduce-site yarn-site and you can also copy the slaves file. All the files have now been added to the new machine, which in turn will be added to the cluster. You can check and see if you have the name node path in the core file. You can see that the HDFS file needs some modifications. Remove the metadata path from the HDFS file. Change the data to data 3 to make it the third data node and save it. The yarn file doesn't require modifications, nor does the MapReduce file, which has the same framework as yarn. After checking if all the properties of the machines are fine, type sudo iptables-flush followed by sudo service iptables stop. Then sudo checkconfig iptables off to ensure that the firewall doesn't block the connection. Type sudo mkdir/simplyl as mentioned in the HDFS file. Type sudo chown -R hduser to change the ownership to hduser. All these steps were previously performed for other machines. The new machine is now ready to be added to the cluster. In the M1 machine, run your script again. Search for the script using the up arrow and execute the appropriate script. Type cd to ensure that you're in the right directory. Go back so that you are in usr/local/Hadoop. If the script doesn't run, go to the home directory and then run the script. Here, you can observe that the name node has now declared the data node as dead. Running the fsck command shows you that your one set of blocks are under-replicated, as the name node could not get the response from the other data node. In the M2 machine, come out to the usr/local/Hadoop path and type sbin/hadoop-daemon.sh start data node. As soon as you start the data node, it will refer the core file and try to communicate with the name node. Type sbin/yarn-daemon.sh start node manager, which will start the node manager and also refer the source file. Check the logs to find out why the daemons have not come up. You can view different logs. Type cat hadoop-hduser-datanode-m2.log and press Enter to go into the data node related log. You will see the java.lang internal error message, which indicates that the packages are not updated. Log in as root and type yum update to update the packages. This process might be time-consuming. Once the packages are updated, you can start the data node and node manager. As soon as the data node communicates with the name node, it will create the missing replicas, and M2 will now be considered a part of the cluster. You can individually start the data node and node manager based on the core file content in the yarn-site file. Machines will find and communicate with the name node and the source manager. Name node will consider this machine as part of the cluster. However, there is no entry of the machine in the slaves file, so you will not be able to perform a stop all on the daemons or use a stop script. Start the M3 machine. If the blocks are replicated to the new machine and you start the daemons on the existing machines, data node will send the block report to name node. This might result in over-replicated blocks. However, the name node will delete the extra set of blocks. Log into the M3 machine. You'll have to wait till the packages are updated to the new M2 machine. Log into the failed machine, which has no daemons running as HD user. If you give a JPS command, it will show you that there are no daemons running. Type sbin/yarn-daemon.sh start node manager. You'll need to be in the Hadoop path for this command. Type cd/usr/local/Hadoop to be in the Hadoop path. Type sbin/yarn-daemon.sh start node manager. Start secondary name node by typing sbin/hadoop-daemon.sh start secondary name node. Type sbin/hadoop-daemon.sh start data node to start the data node so that it communicates with the name node. This will indicate to the name node that the machine is active and the blocks are not under-replicated anymore. Type JPS to show the daemons of the machine that had failed previously. You'll find that all the daemons are now active. Log into the M1 machine. Clear the existing script and run your monitoring script. This will show if the name node has registered the machine that was activated. you'll see that both M1 and M3 is active, and the blocks are not under-related anymore. Once all the packages are updated in your M2, you can again start your data node and node manager. In this demo, you have learned how to add and remove machines in an ad hoc way. Commission or decommission a data node in Cloudera cluster. In this demo, you will see the steps to commission or decommission a data node from a running cluster. Commissioning or decommissioning might be required when you want to add a new machine to a cluster, or if you want to remove a machine from a cluster. Commissioning refers to adding a node or a host to a cluster, and decommissioning refers to not using a particular machine to act as a data node. These activities affect the storage and performance of a cluster. Let's first click HDFS. And in this system, you can see 3 data nodes running which support the replication of 3 nodes. You can click Actions to view the actions related to the service. You can always click Instances to view the roles that run on different machines. You can also see that the commission state is given as commissioned for all role types. Next, let's see how to decommission a data node. To decommission the data node, which is currently running on the machine with the IP address 10.0.0.147, select the checkbox against that data node and click the Actions for Selected 1 drop-down list. Select the option Decommission, and you will see an alert message asking you, are you sure you want to run the decommission command on the following roles? The decommissioning process might return errors or alerts because if the replication is set as 3 and there are 3 data nodes, decommissioning a data node will leave the blocks under-replicated. However, click Decommission. Next, you can see the ongoing steps for decommissioning. The step which says Adding Data Node Hosts to Decommissioning List refers to adding the entries of the nodes to a particular file which is used to recommission machines. Then, you can see the steps that say Refreshing Name Node and Waiting for Decommissioning to finish. The decommissioning function will mark the node as decommissioned and will stop the roles of the data node. Thus, after this process, the data nodes on the IP address 147 will not be active, and that will leave the blocks under-replicated. The cluster will not use the 147 machine to store and process the data. If at any point there is an error during the decommissioning process, you can do a commissioning of the node. Decommissioning and commissioning may sometimes take a long time, as the blocks can be under-replicated. While the decommissioning is still under process, let's go to the terminal and set the replication of all the nodes to 2. Type HDFS DFS hyphen setrep hyphen R hyphen W 2 /, and the replication will be set across all clusters. Let's go back to the admin console. Since you have entered the command for replicating the blocks to 2, the name node will delete one set of blocks from one of the machines. Once the blocks are deleted, the roles are marked as decommissioned and stops the data node roles. Thus, when decommissioning is complete, you have a cluster with 2 data nodes. To check whether the replication is complete or not, go back to the terminal. You will find a warning message stating that the waiting time may be long for decreasing the number of replications, as the name node has to delete one set of complete blocks. You can view the decommissioned status of the 147 machine under the commissioned state. Presently, this machine has no data node that runs on it. To check the status of the data nodes, click Status, and you can view the status summary for the data nodes. For this machine, the 2 nodes are in good health, and 1 machine is in stopped status. To revert the current status, click Instances and select the machine which is decommissioned. Click Actions for selected 1 and select Recommission from the available options. If you are sure of applying the recommission command. Once you apply recommission, the data node that was decommissioned will be back on your cluster. As you have seen earlier, for decommissioning a node, you can see the details for the recommission command as well. The steps that are performed are unblacklisted data node roles, refreshing name node roles, and marked data node roles as commissioned. Click Close, and you will see the recommission command will return the decommissioned data node under the commissioned state. Since the state of the recommissioned machine is displayed as stopped, to restart it, select Start from the Actions for Selected 1 drop-down list. This will start the data node on the specific machine. This is how you can decommission a data node from a cluster. To commission a new data node from a machine, that machine should be allowed to be part of your cluster. The rest of the steps are similar to the decommissioning of the data nodes. Currently, there are 3 data nodes in this machine, and you have seen the steps related to decommissioning and recommissioning. An important point to remember is that if decommissioning takes time, it may be because the name node is searching for one more data node to replicate the blocks. This brings you to the end of this demo. You have seen the steps for commissioning, decommissioning, and recommissioning a data node in a cluster. Decommissioning and commissioning nodes in Apache Hadoop cluster. In the earlier demo, you learned how to add or remove machines in an ad hoc manner in Apache Hadoop cluster. In this demo, you will learn how to decommission and commission nodes in Apache Hadoop cluster. This is the systematic way, and it communicates with the name node in case a system fails or if systems are added. To start the cluster, type sbin/start-dfs.sh, which will start the name node, the data node, and the secondary name node. To enable the commissioning and decommissioning of nodes in Apache Hadoop cluster, you need to have appropriate configuration properties in the configuration files. After starting the storage-related daemons, start the yarn-related daemons by using the command sbin. It starts Resource Manager and Node Manager. Type JPS on the M1 machine to view all the daemons running on M1. Type SSHM3 to check the daemons running on M3. To enable commissioning and decommissioning, you need to add properties to HDFS and the yarn-site file. On the M1 machine, change the directory to etc/Hadoop, which has the config files. Type ls to view the config files. Create 2 files, include and exclude, by typing vi include and vi exclude respectively, and keep both files empty. Type vi hdfs-site.xml to edit this file to have a property that points to include and exclude. This will enable you to include and exclude machines as required. These commissioning and decommissioning processes are also required in order to keep track of machines added to or removed from the cluster. If machines are added and removed frequently, it becomes difficult to track without appropriate documentation. Edit the HDFS file to add the first property using the command property name dfs.hosts.include. This will point to the currently empty include file. Add the value /user/local/hadoop/etc/hadoop. Close the value tag and close the property. Add the second property to point to the exclude file to indicate the machine to be excluded from the cluster when you want to decommission it. Type dfs.hosts.exclude and give the value /user/local/hadoop/etc/hadoop. Close the value tag and close the property. Copy these properties and save the file. Edit the yarn-site.xml file and implement these changes in the machines where the name node and resource manager are running. Paste the two properties copied previously in the yarn site file. To edit, look online for the yarn-related properties. The property for include is yarn.resourcemanager.nodes.include-path. And for exclude, it is yarn.resourcemanager.nodes.exclude-path. Update these properties in the yarn-site file. Save the file. Since you have made changes to the HDFS and the yarn-site file, restart the name node and resource manager. This step will not be necessary in future as the properties are already included. Type sbin/hadoop-daemon.sh stop name node. Type sbin/yarn-daemon.sh stop resource manager. To start the name node again, type sbin/hadoop-daemon.sh start name node. To start the resource manager again, type sbin/yarn-daemon.sh start resource manager. You have started the cluster-related master daemons. After editing the config files, ensure that the replication consistency is not affected during decommissioning. This is not an issue if there are many data nodes. Unless the name node finds another machine where it can place the blocks, it will not decommission the current machine. If you perform commissioning and add another machine to the cluster, the name node will then allow the decommissioning. Start M2 machine so that it can be added to the cluster. Log into the M1 machine and type hdfs dfsadmin-report, which will show you the number of data nodes. To decommission the data nodes, type cd etc/hadoop. Edit the exclude file by typing vi exclude. Mention M3, the name of the machine you want to decommission. The only difference between removing machines in ad hoc and in systematic manner is informing name node. Once include and exclude is updated, the property is reading these files. You would need to inform the cluster that there is a change made to include and exclude. Type HDFS dfsadmin refresh nodes, which informs the cluster to look for changes in files such as include and exclude files. type cd hadoop/etc/hadoop to check the config files. Type vi hdfs-site.xml and point the property commands towards include and exclude files. Type vi yarn-site.xml and point the property commands towards include and exclude files. Since you are making changes to the config files, restart the name node and resource manager again so that these changes are registered. Type sbin/hadoop-daemon.sh stop name node. Type sbin/yarn-daemon.sh stop resource manager. To start the name node again, type sbin/hadoop-daemon.sh start name node. To start the resource manager again, type sbin/yarn-daemon.sh start resource manager. Type hdfs dfsadmin-report. You don't need to refresh, as you have restarted the name node and resource manager. You will see decommissioning in progress status for machine M3. The name node will not deactivate the data node, as there are no other machines available. To commission a machine, type cd etc/hadoop followed by vi include to edit the include file. Add another machine to the cluster, M2, which already has all the config files updated and has SSH access to M1. Type hdfs dfsadmin refresh nodes. Type yarn rmadmin refresh nodes. Type hdfs dfsadmin-report. It shows that 6 blocks are under-replicated. Communicating with the name node will not suffice. You need to log into M2 and manually start the data node and the node manager, which will then contact the name node. Once the name node is informed about the new data node, it will then decommission M3 completely and transfer the block from M3 to M2. Log into the terminal as HD user. You can compare the config files to check that they are pointing to the right name node and resource manager. Type sbin/hadoop-daemon.sh to start data node. To start a node manager that communicates with the resource manager, type sbin/yarn-daemon.sh start node manager. In the M1 machine, type hdfs dfsadmin-report. You'll see that the M2 machine has already started responding to the name node and that the M3 machine has been decommissioned. Type cd etc/hadoop. Update the slave files using the command vi slaves. Remove M3 from the file and enter M2. Updating the slaves file is important so that you can start the daemons on different machines using the start scripts. Otherwise, you'll have to start the daemons individually. Type vi include and empty the file. Type vi exclude and empty the file. Emptying the include and exclude files is important, as it ensures that if you add or remove the same machines again, there is no conflict. Whenever you make any changes to include and exclude files, give a refresh command. Type hdfs DFS-admin refresh nodes. Type yarn rm-admin refresh nodes. Type sbin/stop-dfs.sh, which will stop the daemons based on the slave file and will stop the cluster. This ensures that your start and stop command is picking up the entry from slaves. When commissioning and decommissioning is done, it is advisable to give a balancer command that ensures that the blocks are evenly distributed across the cluster. This is the process of commissioning and decommissioning. In decommissioning, you inform the name node that a machine will be taken down. In commissioning, extra machines are added and name node is informed.
An uneven distribution of data across data nodes could be the result of any of the following: commissioning or decommissioning of nodes, sudden and multiple failures of data nodes, name node not receiving heartbeats from the data nodes due to unknown issues, sudden failure of multiple data nodes and missing or delayed heartbeats from data nodes both force the name node to start replicating data on existing nodes. This results in a huge increase in network traffic and leads to a phenomenon called replication storm. Moreover, if the failing data nodes have more data than the other nodes, it may result in cascading failures, as more data needs to be replicated, causing overload on existing machines and resulting in their failure. Failures could be due to regular events or catastrophic events. A regular event depends on the rate of failure of data nodes, whereas catastrophic events could be due to network issues, rack failures, or massive hardware failures. Regular events do not cause any major impact. For instance, in a cluster of about 3,000 nodes, only 2 data nodes might fail per day. On the other hand, catastrophic events trigger the loss of hundreds of nodes within a few minutes. These cause performance issues, as well as failed tasks and applications. To understand how a replication storm could occur, let us go over an instance that happened in an organization. A bad job started creating millions of files within a few minutes. This caused the name node to become sluggish because it had to run many create transactions and was, therefore, unable to process heartbeats from data nodes. The cluster comprised 3,000 nodes, and 1,000 of them lost heartbeats, resulting in a replication storm. The HDFS balancer helps to evenly distribute data and avoid these problems. It balances or rebalances data across the data nodes by moving blocks from overutilized nodes to underutilized nodes. This can be beneficial when data nodes are commissioned or decommissioned, when data nodes fail suddenly, or even when the name node stops receiving heartbeats from data nodes due to unknown issues. Let us now see a demo of how to balance or rebalance a cluster to ensure an even distribution of data. Using Balancer to balance data in Hadoop cluster. In this demo, you will learn how to balance data in Hadoop cluster using Balancer. One of the requirements of a cluster is to distribute data evenly across the nodes. Even when you perform commissioning or decommissioning, or while adding or removing a host, it is important to distribute the data or balance the data load evenly across the cluster. In HDFS utility, you can observe that a balancer is already running, which takes care of balancing the data. Balancing is required whenever you add a new cluster, deploy client configurations, add some role instances, and commission and/or add more data nodes to take care of your data. In order to balance the data, you need to go into the terminal and type SSHM1, which takes you to the first machine. You can give the balancing command from any running machine by logging in as root and then log in as HDFS, which has the administrator access on the cluster by default. You can type HDFS in the terminal, which gives all the options that can be given, along with the HDFS command. There is an option Balancer, which runs a cluster balancing utility. This moves the blocks from overutilized machines to underutilized machines. In order to move the data from overutilized machines to underutilized machines, you need to type the command HDFS Balancer and click Enter. You can also give a command for threshold as hdfs balancer-threshold. This expects a disk percentage. In this case, we give it a 75, so the command is -threshold 75. If we give threshold along with percentage, the balancer task is performed when the storage exceeds 75% of disk space. In order to check the number of data nodes that are working, you need to type the command as hdfs dfsadmin-report. This shows the number of data nodes that are present. In this case, we are using 4 data nodes. Disk balancer is used to balance the data in disks within a node. This command can be used when multiple disks are configured to a node. For this command, you need to type hdfs disk balancer. Now you can find multiple options on the screen for further actions which you want to perform. When there are multiple disks, you will be prompted to provide the name node path, where the name node is running. You can also give a threshold percentage based on your requirement. This brings us to the end of the demo on balancing data evenly on a Hadoop cluster.
Some core services are added to the cluster during the initial setup. However, services can be added to or deleted from a cluster. Services can also be started, stopped, and their status can be checked. In this topic, we will cover how services can be managed in a cluster. The wizards in Cloudera make it easy to manage services. Now that you have learned to set up a cluster, you will learn how to add new services to the cluster. Go to Cloudera Manager and click Clusters. Choose the cluster in your machine, which would show the existing services on the left side of the screen. On the right side of the interface, you will find Actions. Click it and select Add Service. This brings up the Add Service wizard, which displays the different services that can be added to a cluster. You can select any service from the list of services that are shown here. Let's add Scoop 2. Scoop is a tool which is used to import and export data from structured data stores. Click Continue. You can see a screen in the wizard that says, Customize Role Assignments, which will ask you the locations where you would want to place the Scoop server. By default, it will show you a location. Click it. In the next screen, you will see that a few roles are already assigned to the server. Uncheck all the hosts and select the last host name to place the server in the machine with the IP address 10.0.0.149. Click OK. Next, click Continue, and based on the settings, the wizard will display the default configuration files and databases and the location of the Scoop repository. You can retain these default settings or change them according to the requirements. Click Continue. Now, the wizard will set up the Scoop user directory. It will create the Scoop database and start the Scoop server in the cluster. Once it's done, you can click Continue, and the Scoop-related service will be added to the cluster. If you want to view the steps while the server addition process is going on, you can click the arrow near Start. Once the process is complete, click Continue. Now you can see a message that the new service is installed and configured on your cluster. The message also provides certain additional information related to new and existing services. It informs that you may have to start the new service for it to work, and it is recommended that you have to restart any additional dependency services which have with outdated configuration settings. Click Finish. Once the service is added, you will see it under Cluster 1. You can click Scoop to check the instances that it is running and the machines that it is using. Click Instances, and you can check the role that is running currently. Click Configuration to check or edit any configuration settings. You can always look in Quick Links to check errors.
So now that we have added a scoop-related service, you can also add another service in a similar manner, and these services will be listed under the cluster name. At any point of time, if there are any alerts related to a service, configuration, or specific issues, you can click Configuration and make the required changes. This brings us to the end of this demo. In this demo, you have learned the steps to add a service to a cluster. Now that you have learned the steps to add a service to a cluster, in this demo, you will learn the steps to remove a service from a cluster. Let's remove the service Scoop2. Click it, and on the next screen, click Actions and select Stop. The following message will be displayed on the screen. Are you sure you want to run the stop command on the service Scoop2? Click Stop, and the process to stop the service will start on the next screen. Once the activity is completed, click Close. Now you can similarly stop other services, except Scoop Client, as only services can be stopped in a cluster. Now to remove the service Scoop2, you have to go back to the cluster and in the list of services, select Scoop2 and click Delete. A warning message will be displayed, asking if you are sure that you want to remove the service from the cluster. Further, the message informs that the service data will not be removed from your host machine, but will be removed from the Cloudera Manager. Also, all the role groups under that particular service will be removed from the host templates. You may ignore the message and click Delete. You can similarly delete any other services. In this case, we can delete the Scoop client since we do not have the Scoop server. This brings you to the end of this demo, where we have learned the steps to delete a service from the list of services in a cluster. Starting and stopping of services should be done in the correct order because of the dependencies they may have on other services. For example, MapReduce and Yarn have a dependency on HDFS, so you must start HDFS before starting MapReduce or Yarn. Note that the Cloudera Management Service and Hue are the only two services on which no other services depend. You can start and stop them anytime. But there is a recommended order that needs to be followed. Follow these steps to start or stop services within the Cloudera Admin Console user interface. Select the Cluster tab, and then select Services. On the list of services, select the service, and then on the drop-down list next to a service name, select Start, Stop, or Delete as required. Note that the Admin Console shows the depending services and prompts an action on them before proceeding with the starting, stopping, restarting, or deleting of a service. We learned that the order of starting and stopping services is important. Let us now note that order. The following is the order that needs to be followed to start services: Cloudera Management Service, Zookeeper, HDFS, Solar, Flume, HBase, Key Value Store Indexer, MapReduce or Yarn, Hive, Impala, Uzi, Scoop, Hue. The following is the order that should be followed to stop services: Hue, Scoop, Uzi, Impala, Hive, MapReduce or Yarn, Key Value Store Indexer, HBase, Flume, Solar, HDFS, Zookeeper, Cloudera Management Service. When you enable a new feature or when you make any changes to the configurations of a service, it usually requires restarting the service. We will now view a demo on starting, stopping, and restarting services. In this demo, you will learn the steps to start and stop a service in a Cloudera cluster. To perform this demonstration, we have a cluster running, and you can start or stop a service with a click. To stop all the services, click Actions and select Stop. This will stop all the services in a particular order. So we can stop the cluster by stopping all the services. And we can view the order in which the services are stopped. Starting of services will be in the reverse order. So if it first stops Hue, then Uzi, next Hive, then Yarn, HDFS, and finally it stops Zookeeper. Click Close, and you can see that all services have status as stopped. You can individually start a service by clicking the drop-down list near the particular service. Click Start, and the wizard prompts us to also start the related dependent services which depend on our service under consideration. You can also start all the services by clicking Start from the Actions menu. Once you click Start, it will display an alert message whether you want to run the start command on the cluster. This will start all the services in an opposite order of stopping the services. Thus, it starts the Zookeeper first. Next, the HDFS, Yarn, then Hive, Oozy, and then Hue. You can click Close and let the start process work in the background. You can always click a particular service and check the activities that take place and view the details while the start process is going on. Once the services are started, it displays the status as green against each service. The status will display an alert against the service if any problems might arise with the upcoming services, or if the services could not acquire the right information. The entire process will take some time, and you can see that when most of the services are starting up, the status is shown as green. So, as you have seen, you can always start and stop the services one at a time, but you will receive an alert message asking whether you want to start or stop a dependency service. Let's just wait for all the services to restart. While changing the configurations, we might have to individually start or stop a service based on the alerts. We can look into Diagnostics and select Logs to view the logs related to different roles on a particular host, and we can even search for logs with specific error messages. Now all the services have started, and you can view that in status. If you want, you can stop a specific service by clicking Stop in the drop-down list near a particular service. If we select Hue, as in this case, the service will stop because it depends on all other services. Moreover, you will not receive any alert message. Next, click Close. Stopping those services which are not used currently is sometimes useful, as this reduces the load on the cluster. What are referred to as services in Cloudera are called open software packages. Hadoop. Let us learn how to add, remove, start, or stop the open software packages in Apache Hadoop. To add or start open software packages in Apache Hadoop, you need to perform the following tasks. Download the tar file of the relevant software package, such as Hive, HBase, Spark, Hue, Flume, Scoop, Oozy, and so on. Untar the file in a particular location in the file system. Install JDK, NTP, SSH, and other relevant packages. Ensure communication across nodes. Update the path of the package in What are referred to as services in Cloudera are called open software packages in Apache Hadoop. Let us learn how to add, remove, start, or stop the open software packages in What are referred to as services in Cloudera are called open software packages in Apache Hadoop. Let us learn how to add, remove, start, or stop the open software packages in Apache Hadoop. To add or start open software packages in Apache Hadoop, you need to perform the following tasks. Download the tar file of the relevant software package, such as Hive, HBase, Spark, Hue, Flume, Scoop, Oozy, and so on. Untar the file in a particular location in the file system. Install JDK, NTP, SSH, and other relevant packages. Ensure communication across nodes. Update the path of the package in .bashrc. Edit configuration files. Start the daemons on all nodes or on each node individually. To stop or remove open software packages in Apache Hadoop, you need to perform the following tasks. Stop daemons. Delete the untarred package files. The replication algorithm places blocks on appropriate nodes. To do this efficiently,
it is important that the algorithm knows which rack the nodes belong to. Providing the rack information to the replication algorithm can be done by enabling rack awareness. In Cloudera, you can enable rack awareness through the admin console by following these steps. First, create a topology file that contains information about which racks nodes belong to. Select Hosts, Data Nodes, and then select Assign Rack. Restart the HDFS service. In Apache Hadoop, you can enable rack awareness by updating the hdfs-site.xml file with the property topology.script.file.name and including the path to the topology.sh script file. In the topology.sh script file, include the node to rack mapping. We will now view demos on enabling rack awareness in Cloudera Cluster and Apache Hadoop Cluster. Enabling rack awareness in Cloudera Cluster. In this demo, you will learn how to enable rack awareness in Cloudera Cluster. Rack awareness is an important configuration which ensures that the blocks are placed on the machines. Rack awareness makes sure that all data blocks or all replicas of data do not reside in data nodes on the same rack. This ensures high availability of data and also benefits the data nodes by providing higher bandwidth in the same rack. To enable rack awareness, click on Host, then on All Host. This will display different hosts. You can select the hosts in such a way that you can assign each host to a different rack. In this case, select the first and second hosts, and then under Actions for Selected, click on Assign Rack. Now it will prompt you for a rack name. Let's give the name as /rack1 and click on Confirm. Similarly, assign the other two hosts to /rack2. In order to confirm that the hosts are assigned to racks, click on Rack. You can see Rack 1 and Rack 2, which are just created. If you click on each rack, you can find the details of hosts which are assigned to the respective racks. You can also check this using terminal by typing hdfs dfsadmin-report. This will display all the details of data nodes that are present in a cluster. The rack setting is default, which means that the services need to be started by adding clusters which have data nodes placed on the racks. In order to start the services, you have to go into Cluster 1, which is just created, and beside HDFS, you will find a refresh icon. Click on the refresh icon to reflect the changes on HDFS. It will then display all the changes that are done. Then click on Restart Stale Services. Once you click on Restart Stale Services, it will ask you to review changes. In this case, you enable the Rolling Restart and also all the options under Services to Restart, Rolling and Basic. Once you enable the options, click on Restart Now at the bottom right. This will restart the services which have been affected due to recent changes. You can also go to Action tab and perform a restart of all the services. When you do a restart, first, all the affected services will be stopped, and then it will start the services in an order, which helps in enabling the rack awareness correctly. The process will also involve arranging of blocks in data nodes as per their placement in rack. Currently, it is starting the Hue service, followed by Uzi, Yarn, HDFS, Zookeeper. Then it will deploy the client configuration, and next it will run a command for rolling restart. If you are asked to do the same in Apache Hadoop cluster, you have to add some properties in the config files. Then point the properties to a file which has the entries of IP address to rack, and enable the rack awareness. Once the restarting is done, click on Finish, and then check whether the data nodes are placed on the racks that are created, rather than being on the default rack. You can also look into the data path in order to check if the blocks are evenly placed across the cluster. If required, you can issue a balancer command to distribute the data evenly across the cluster. Now, let us check in the terminal using the command hdfs dfsadmin-report. You can find that the machines are assigned to the respective racks. You can check the cluster status where the machines have been placed on racks. Finally, rack awareness is enabled in cluster. This brings us to the end of the demo on enabling rack awareness in Cloudera cluster. Enabling rack awareness in Apache Hadoop cluster. In this demo, you will learn how to enable rack awareness in Apache Hadoop cluster. As you can see in the terminal, the cluster is running on two nodes, which are M1 and M3. These are the daemons that are running on M1, and these are the daemons that are running on M3 machine. Now, you will log into M1 machine and type hdfs dfsadmin-report. This will show the data nodes that are running on a cluster. As you can see, there is no information about any machine being on a particular rack. To enable rack awareness, type vi topology.data. Here, you need to provide the IP address. Type 192.168.1.196 for M1 machine, 192.168.1.197 for M3 machine, and 192.168.1.198 for M2 machine. You enable all the three machines, and in this case, the cluster is running on M1 machine. In order to add machine M2 using terminal login as HD user, go to My Hadoop path cd usr/local/Hadoop, and then start
my data node and data node manager by typing sbin/hadoop-daemon.sh start data node and sbin/yarn-daemon.sh start node manager. Once you start data node and data node manager, go back to the terminal and type hdfs dfsadmin-report. Now you can see that there are 3 data nodes that are part of the cluster. To place the machine on rack and to have blocks placed efficiently, the topology.data file is created, which has the entries of all 3 machines. Even if you add any new machines, that data should also be added into the topology, else you cannot add the data nodes into the cluster. Once you have updated topology.data file, go to Hadoop config file using cd usr/local/hadoop/etc/hadoop and add a property in HDFS file by typing vi hdfs-site.xml. You can now add a new property to point to a particular file using command property. Enter the name. Here it is given as name, topology.script.file.name, name. Give the value as value/usr/local/hadoop/etc/hadoop/topology.sh value and close the property tag property. If you do not have a topology file in config files, create one using vi topology.sh and save the file. In order to make it executable, type chmod-r 777 topology.sh. Now you can find the topology file. To read the topology.data file and to enable rack awareness, log in as root and change the directory to the folder where we have the file. Here we have the file in downloads. So the script will be cd/home/m1/downloads/. Next, go to cat hadoop/essential/cmds/or/parameters.txt. By doing this, you can check the content in the respective text file. Here, let's check the content for topology.sh. This is a simple bash script, which reads the entries from topology.data file and compares with the IP address of machines and helps them to be on the rack. Let's copy the content for topology file. Once the content is copied, log in as an HD user and go to the path where there is the topology.sh script, which is
/usr/local/Hadoop/etc/Hadoop. And in order to go to the script, give the command as vi topology.sh and enter the copied script. Now change the home as /home/hduser/topology.data. The script is read line by line. It will compare the entries in topology.data file with the entries of IP addresses of the nodes. If it finds a matching entry, it will let the cluster know about the machine and its rack. If it does not find a matching entry, it will show as default and save it. Now, let us place the machines on racks. For rack awareness, make sure that all three machines should be on the same rack. So place each machine on individual rack. Here, let's place M1 in /rack1. M3 in /rack1. And M2 in /rack2 and save the file. Since changes are made to the HDFS file, let's give the property as topology.sh, which reads topology.data file that the cluster is also running. To start the name node, give the command cd/usr/local/Hadoop, and, as you have to restart the master services, give the command as sbin/hadoop-daemon.sh stop name node. Then, you will start the name node with command sbin/hadoop-daemon.sh start name node. Once you start the name node, it will recognize the new property, which is given in HDFS site file. The property points to topology.sh script. The script reads from topology.data and compares the data with node IP addresses. So now use the command hdfs dfsadmin-report. By doing this, you can find the machines in the assigned racks respectively. Based on this, the blocks will be placed on the machines, which ensures that all the replicas of particular blocks are not placed on the same rack. Now you have come to the end of the demo on enabling rack awareness in Apache Hadoop cluster.
Once you add a service, you can add a role instance to it. To add a role instance, you have to do the following. Select the Services tab, and then select the service to which you want to add a role instance. Select the Instances tab. Click Add. Follow the instructions given by the wizard to add the role instance. The Cloudera Manager lists existing roles on hosts and also recommends configuration settings and changes. Make the changes you require, and then click Continue or click Skip and use the recommendations. The wizard completes the necessary actions to prepare the cluster for the new role instances. The new role instance is configured with the default role group for its role type. To change the role group, on the Role Groups page, under the Configuration tab corresponding to the service, select a different role group for the role instance. On the Instances page for the service, start the role instances. Note that the role instances are not started automatically. The procedure to decommission or recommission a role instance is the same as the one followed to decommission or recommission a data node. To delete a role instance, select the Services tab, select Instances, and on the list of actions, click Delete. Adding role instances to the Cloudera cluster. In this demo,
you will learn how to add role instances to the Cloudera cluster. You have seen earlier how to add a new host to the cluster where no roles are assigned. In this demo, you will see how to add role instances to the machine. Click Cluster and choose Cluster 1. Now choose HDFS service from the status list. As you can see, the HDFS service has 3 data nodes, and now you will add the 4th data node as a new role instance for the 4th machine. Under the Instances tab, click Add Role Instances. The Customize Role Assignments page will ask you what are the role instances that you would like to add. Now click Data Node and click Select Hosts and select All Hosts and click Continue. In the Review Changes page, you can see the data node running on the new host. Click Finish. You have now added a data node instance on the new machine. Select the data node instance. Check the box next to the role instance and click Actions for Selected 1 and choose Start from the options. This will start the new data node instance on the new machine. In the Details page, after the data node instance has started, click Close. Now, the data node instance will be added to the cluster and to the new machine. Note that to remove a particular role instance, check the box next to the role instance. Click Actions for Selected and choose Stop from the options. Now, let us go back to the cluster, Cluster 1. Click Actions and choose Restart from the options. Note that another way to add role instances is to go to the HDFS service from the cluster and click the drop-down button next to it and choose Add Role Instances. Now, in this demo, you have learned how to add role instances to the Cloudera cluster. Let us now learn how to manage hosts. You can add one or more hosts with the Add Hosts wizard. This wizard will install the Oracle JDK, CDH, Impala, and the Cloudera Manager agent packages. Once the packages are installed and the Cloudera Manager agent is started, the agent connects to the Cloudera Manager server. You can then use the Cloudera Manager admin console and monitor CDH on the new host. To add one or more hosts, select the Hosts tab and then click Add Hosts. The process of searching and selecting hosts is the same as the process for setting up the cluster. To find hosts that Cloudera Manager already recognizes, but no roles have assigned to them, navigate to the Cluster Managed Hosts tab and then select the host. Verify if Cloudera agents on the new hosts connect with the Cloudera Manager correctly. Verify if the health status is fine for newly added hosts. Note that the Add Hosts wizard does not create roles on the new host. Once you have added the host, you can add roles for each service, or you can apply a host template, which defines the role configurations for multiple roles. The procedure to decommission or recommission a host is the same as the one followed to decommission or recommission a data node or role instances. To delete a host from the cluster, but keep it available for other clusters, first, stop Cloudera Manager from managing the host, and the Hadoop daemons on the host. Then, perform the following actions. Select the Hosts tab. Select the host that you want to delete, and then on the actions list corresponding to the selected host, click Decommission. Click Stop Agent on Host. This ensures all roles on the host are stopped. Select the Hosts tab. Select the host you want to delete, and then click Delete. Adding hosts to the Cloudera cluster. In this demo, you will learn how to add hosts to the Cloudera cluster. Before you add a host or a machine to the cluster, some applications such as Java and NTP service have to be installed. You need to make sure that it has the secure shell or SSH with other machines. Also, make sure that the NTPD service on the machine has been started. Now, go to the cluster admin and click on Hosts and All Hosts, which will show you all the hosts that are already available. The following steps will explain how you can add a new host to the cluster. Click on Add New Hosts to Cluster, which will take you to Manage Clusters on EC2. Now, click on Classic Wizard, and then select Continue. On the Specify Host for our CDH cluster installation page, provide the host name and click on Search. This will show you the machine or the new host that will be added to the cluster. Now, click on Continue. In the Add New Hosts to Cluster, select the Matched Release for this Cloudera Manager server option and click Continue. You will now be able to see the Oracle binary license. Check the box for Install Oracle Java SE Development Kit JDK and click Continue. In the Provide SSH Login Credential page, select Another User and provide the password. Now, select All Hosts Except Same Private Key. To choose the file, click Choose File and select the file and click Continue. Click OK when you get the prompt, Continue SSH Login with no passphrase. The new host or machine gets registered, and the packages will be available in the new machine. The Cloudera Manager agent will also be set up, which has to send the heartbeat to the server. After the installation is complete, click Continue. In the Installing Selected Parcels page, we can see that the parcels are getting activated to the new machine and then get added to the cluster. To know the status of installation of the parcels, click the drop-down button. After the parcels get activated, click Continue. Run through a host inspector, which will warn you about any critical errors. Now, click Continue. You will now have to select a host template to apply the new hosts to populate them with role instances. Check the box Start Newly Created Roles after applying the host template and click Continue. Deploy some client configurations to the new machine. After deployment, click Finish. You will now see that the new machine has been added to the Cloudera cluster. In this demo, you have learned how to add hosts to the Cloudera cluster. In this topic, we will learn about federation and high availability, which are important features included in Hadoop version 2 that help overcome certain limitations of Hadoop version 1.
The first version of Hadoop had some challenges, such as no horizontal scalability of the name node. A single name node meant there was a single namespace ID. It also meant there was only a single RAM. This limited the capabilities of the Hadoop cluster. No high availability of the name node. There was a single name node and no failover mechanism. The secondary name node, which was used to checkpoint and maintain a backup of the metadata, had to be used for a failover. Another option to tackle cluster unavailability due to name node failures was to store the metadata in a disk at another location. Overburdened job tracker. The processing master, or the job tracker, was overburdened. It was the only one listening to all task trackers. It was responsible for handling job scheduling as well as managing resources, and so spent a lot of time and effort in managing the lifecycle of an application. Processing restricted to map and reduce tasks. The Hadoop version 1 cluster could only process map and reduce tasks. It could not handle any other specialized tasks, such as graph processing. This meant that the massive data store on HDFS went unutilized. The Hadoop version 2 includes features which overcome the problems we just discussed. The feature Federation allows multiple name nodes and namespaces. This means more RAM can be utilized. The high availability feature allows active as well as standby name nodes. It facilitates both manual and automatic failover. The Yarn processing framework allows both normal and specialized kind of processing, with the resource manager replacing the job tracker and node managers replacing task trackers. The application master takes care of scheduling and task completion. It also includes schedulers like Capacity Scheduler. Let us understand the features of Hadoop version 2 in detail. First, we will discuss federation. HDFS has two main layers. These are namespace and the block storage service. The block storage service is further divided into two parts called block management and storage. Block management is performed in the name node. The block management service tasks include providing data node cluster membership by handling registrations and checking periodic heartbeats, processing block reports and maintaining the location of blocks, supporting block-related operations such as create, delete, modify, and obtaining the block location, managing replica placement and replication of under-replicated blocks, deleting over-replicated blocks. The data nodes provide storage by allowing storage of blocks on the local file system. It also handles the read and write permissions. As mentioned before, in Hadoop version 1, the HDFS architecture allowed only a single namespace for a cluster. This was managed by a single name node as illustrated by the image on the screen. Hadoop version 2 provides the feature Federation, which provisions horizontal scalability of the name node by allowing multiple name nodes with unique namespace IDs, as illustrated on the screen. These name nodes are independent and don't need coordination with each other. The data nodes are used as common storage for blocks by all the name nodes. Each data node registers with all the name nodes in the cluster. In this topic, we will learn about federation and high. In this topic, we will learn about federation and high availability, which are important features from the namespace volume. When a name node or namespace is deleted, the data nodes store the blocks of all the block pools in the cluster. Each block pool is managed independently of the others. This enables a namespace to generate block IDs for new blocks without having to coordinate with the other namespaces. The list of block IDs can be viewed under Block Pool ID in the data path. If any of the name nodes fail, the data node still continues to serve other name nodes in the cluster. A namespace and its block ID together form the namespace volume. When a name node or namespace is deleted, the corresponding block pool in the data nodes is deleted. A new identifier called Cluster ID is added to identify all the nodes in a cluster. When a name node is formatted, the cluster ID is auto-generated. It should be used for formatting the other name nodes in the cluster. The following are the advantages of federation. It enables horizontal scalability of the name node. It provisions scalability of file systems, thereby delivering higher throughput for read-write operations. It isolates the name nodes and thus enables multiple applications or users bound to specific namespaces to work simultaneously. Another important feature of Hadoop version 2 is high availability, or HA, using the network file system, or NFS. This feature addresses the failover issue of Hadoop version 1 by allowing two machines to be configured as name nodes within the same cluster. One of these name nodes runs as active, and the other runs as standby. At any time, only one of them is active. The active name node handles all client operations in the cluster, while the standby name node acts as a slave and maintains a ready state to provide a quick failover when necessary. The standby name node is always synchronized with the active node, because both have access to directories through a shared storage device. For example, they can both access a network file system, or NFS mount, through a network-attached storage, or NAS. To get more clarity about high availability, observe the image on the screen. The active node performs a namespace modification and logs a record of the modification to an edit log file stored in the shared directory. The standby node constantly checks this directory for modifications and applies them to its own namespace. In case of a failure, the standby node ensures that it is up to date with all modifications from the shared storage, and then takes over as the active node. The standby node switches to active state. In this way, there will be no losses because of the failover. To ensure that the standby node is up to date with block information, the data nodes are configured with the location of both name nodes. They send block location information and heartbeats to both the active node as well as to the standby node. To set up HA for automatic failover, you need Zookeeper, which is a service that handles the maintenance of small volumes of coordination data, notifies clients of any changes to that data, and monitors clients for failures. The Zookeeper Quorum and Zookeeper Failover Controller, or ZKFC, are components that enable automatic failover. Zookeeper helps in failure detection. The name nodes in Zookeeper maintain persistent sessions. If there is a failure, the Zookeeper session expires and notifies the other name node to trigger a failover. Active name node election. Zookeeper identifies a node as the active node. When the currently active name node encounters any issues and ceases to function, another node takes a special, exclusive lock in Zookeeper so that it may take over as the active node. The ZK Failover Controller, or ZKFC, is a component which is a Zookeeper client that monitors and manages the state of the name node. In the deployment, a machine that runs the name node also runs ZKFC. ZKFC helps in health monitoring. The ZKFC constantly communicates with the name node and uses a health check command to verify the status of the name node is healthy. The status of the node is marked healthy if the node gives a timely response and no issues are detected. If the node has ceased to function or has encountered any other issues, the ZKFC determines that the status of the node is unhealthy. Zookeeper Session Management.
If the local name node is active, a special lock called znode is assigned to it. This lock uses Zookeeper's support to handle ephemeral nodes. The znode is automatically deleted once the session expires. Zookeeper-based election. If the local name node is healthy and no other node currently holds the lock znode, Zookeeper contests to take over the lock. If it successfully takes over the znode, then it becomes responsible for making a local name node active during a failover. Another way of setting up HA and enabling automatic failover is by using Quorum Journal Manager. Unlike HA with NFS, when HA is set up with QJM, both the name nodes communicate with a group of separate daemons called journal nodes, or JNs, as shown on the screen. The active name node logs any namespace modification performed to a majority of these JNs. The standby node is capable of reading the modifications from the JNs. The remaining process of high availability is the same as in NFS. Observe the image on the screen to get an overall picture of the architecture in Hadoop version 2. In this demo, you will learn the steps to enable high availability for Namenode and Resource Manager in Cloudera Cluster. Any Hadoop cluster requires stability. You can see the HDFS service, which runs with one name node, and this name node is the master of the cluster. Unavailability of the name node can cause the cluster to go down. It is always preferable to have your name node set up with high availability. This will allow two name nodes to exist, one that is active and one that acts as a standby. If the active name node fails at any point of time, the standby name node will change to active. Let's learn the steps to enable high availability in the cluster. Click Clusters, and then click HDFS service to enter that service. Next, click Actions and select Enable High Availability from the drop-down list. Remember that if you select high availability for a name node, a secondary name node will not be allowed. High availability can be set up in two different ways: by using NFS, which is Network File System, and by using QJM, which is Quorum Journal Manager. Let's see how to enable high availability using QJM and the steps to let Zookeeper take control of the NFS status. Once you select Enable High Availability, you will be able to view a Getting Started wizard. You will receive a message on the screen about the activities that the wizard will help you perform. Enter a name for the Name Service text box and click Continue. Select a host where you want your name node to run. In this demonstration, we will select the host machine with the IP address 10.0.0.149. Click OK. Next, click the host machine for journal nodes. It is recommended that journal node run on machines with a similar hardware specification as the name nodes. Select the Journal Node Hosts text box and select the checkbox for the host machines that have to act as journal nodes. Click OK. Click Continue. The wizard will take you to a screen where you have to enter a value for the Journal Node Edits directory. Journal nodes will store the edits under the Value section. Click the text box and enter the path for the machine with IP address 10.0.0.147. In this demonstration, you will provide the path as /dfs/jn1. Click the next text box and enter the path for the system with IP address 10.0.0.148. Set the path as /dfs/jn2. Enter the path as /dfs/jn3
for the third machine. Once done, click Continue. You can always read the extra options if you want to make any additional changes. When you click Continue, the steps to enable high availability starts one by one. You can see this on the screen. You should always remember that high availability can be set up in two ways, by using QJM and by using NFS, with or without Zookeeper. Similarly, you can also define high availability for Yarn. This might be necessary in order to enable Resource Manager to run simultaneously on two different machines, one that is active and the other is in standby. Now you can see the ongoing last step of enabling high availability, that is, starting the name node on the machine with IP address 10.0.0.149. The next step is to create an HDFS temporary directory if it does not exist. It will start HDFS and its dependent services. Note that at any point of time, if you have made any changes in the configuration files, you might be prompted to start all the services. Once all the steps are complete, the wizard will start the cluster with high availability, that is, dual name node. You can make it more secure by letting the name node store metadata in multiple locations. The start command will start the HDFS service and the UZI service and will deploy the configuration for clients. The last step is to deploy client configuration so the clients can connect to the cluster with a dual name node. Click Continue. In the next screen of the wizard, you will see certain alerts related to HDFS web interface and Hive. You can look at these issues later. Click Finish. Now that you have set high availability for HDFS, you can see a configuration alert under Configuration. Click Configuration to find the issue. You can see the issue on screen, i.e., you need to provide a default group for the journal node edits directory. Click Save Changes. Once your changes are saved, you will be able to see if the services need to be restarted to save the changes that you have made. Wait for some time to check if the changes have triggered the restart of the service or multiple services. Using the steps you learned for performing high availability for a name node, do the same for the Yarn service. In this case, Yarn has only one resource manager running on it. You can click Actions and select Enable High Availability. The rest of the steps are similar. The steps that you have learned in the demo will help you to enable high availability for name node using QJM. You can also enable high availability for Yarn, which will make sure that the cluster will have 2 name nodes and 2 resource managers. This makes the cluster highly stable in terms of processing, data storage, and hardware. Once the steps are complete, click Finish. It is always advisable to restart the cluster after you make a set a high availability. Once you have restarted the cluster, you can check the status under Instances. The status summary will provide you information about the cluster and its activities. You can see here
that there are two resource managers. Note that whenever you provide high availability for any service, you might receive certain errors for that service. You might have to restart the service in such instances. This brings us to the end of this demo. In this demo, you have learned about enabling high availability for a name node and resource manager in a cluster.